From ContainerDays Hamburg, this video is proudly presented by Dux IT.
My session is going to talk about how containers work underneath and what it is that a container runtime does. And we'll also try to do a demonstration and try to build a mini container runtime ourselves in this session. Right. So a quick introduction about myself. My name is Ajitem. I come from India. I've been working for nearly 15 years at this point, and I've been working with Docker and Kubernetes since about 8 years. I am also deep into Golang and related things. You can find my LinkedIn and GitHub for some more experiments and other things over there. And now moving on to our main topic. So what is a container runtime, right? So a container runtime is the foundational piece of software that allows us to run containers within the host operating system, right? It is responsible for doing several things, like it will pull the container image from a container registry that you specify. It will manage the life cycle of those containers, like it will start it up, it will make sure that it's healthy, it's running, and it will also then help you clean it up afterwards. And it will basically do everything that is required to run that container properly on your machine. Now, Docker is not a container runtime, right? It is a container engine because beyond what a container runtime does, it does several other things. And Docker, in fact, uses containerd and runc to make your containers work underneath. So containerd will be the container runtime in this case, right? Docker, like I said, also offers a suite of tools for building, shipping, running, monitoring, and whatnot. It's grown a lot, and it's much more than a container runtime, right? So whenever you do a Docker run on your machine, what it does is it sends a message to the Docker daemon, and the Docker daemon will then instruct containerd to do that action, and runc will actually spawn up the container and manage the lifecycle for it underneath. So it's quite a complex process of what's happening underneath. Now, what actually is a container? So a container is a process that runs on your system. It runs in an isolated environment using cgroups and namespaces. And it also has a root file system associated with it. So the root file system could be of an operating system, or it could also be your application directly, right? So a simple definition here would be that a container is essentially the file system which signifies what to run, right? And namespaces provide the isolation, cgroups provides the sharing, and they together signify how exactly that application or whatever is in that root system is to be run. So cgroups, right? So cgroups is a Linux kernel feature for resource accounting and limiting. So it can be thought of as budgets for your processes. So like we all have our financial budgets, or we have our budgets for maybe something like our screen time or something like that. So the kernel process also needs to manage the budget for your CPU execution time, IO, right, memory. So this is where cgroups comes into the picture. Using cgroups, you can control the amount of CPU that the process can consume. You can limit the amount of memory that can be accessed by the process, and then it can also continue to an extent the IO, the disk, or the network bandwidth of the associated system. Cgroups are organized as hierarchies of directories and files. So basically, you will have a root cgroup, which will have a system slice, which will contain all of your system processes. Like for example, in this, we have the SSH daemon or the Nginx web server, and then you have application slices, like you can have a slice for your Docker, or your application can also have its own slice, should you wish to create. And through this slice, you can apply all these resources limitations, right? The limits are applied per group and not per process. So like if you have a C group slice and you have, say, 5 processes in it, so all the resources and all the limits will apply collectively to those 5 processes, and it won't be like per process in that group. Now, before moving on to what namespaces are doing, we can do a quick run of how the C groups work. And to help with that, I have created a bash script. So in this bash script, what we are doing is I'm creating my own slice and my own scope for this purpose of the demo so that I won't touch anything that is of harm. We'll be basically creating a C group which will allow a maximum of 5 processes to execute at any given time. So this is where we are setting it here. So we have to write that number to a file, and it will tell you how many processes it can run. So we are limiting it to 5 processes. And then the most important thing is you have to move the parent process into that C group. So what happens is once you move the parent process into a new C group, any child processes spawned from that parent will automatically be a part of that C group. So this is important. And then this is a simple few lines of code to spawn 10 processes. So each process will live for 5 short seconds and it will terminate. And there is some other functions for status, like you can see what is happening. And then there's some functions for cleanup. So when we execute this, I also want you to pay particular attention to the output of this script, right? So just for a recap, we are limiting to 5 processes, right? But if I execute this, you'll see that I am only able to spawn 3 processes at a time, right? And then I'm getting an error, and then after those 3 exit, I get 3 more processes. Now, why this happens is because if you notice at the top, you have 2 PIDs. So PID 5 is my bash process, and the second one, which is executing, is actually the for loop, which is actually spawning all the process. So those 2 slots were taken away from the limit of 5, and we were left with 3 slots. So at any given time, we could only invoke 3 processes. So the first 3 invoked, then the next 3, then the last 3, and then the last process. So this is how your typical container, or like even if you're configuring this in your Kubernetes cluster, so this is how they manage how many processes your application can spawn. And this is also a very good way to limit your application from certain attacks like, fork bombing and shell bombing. So if you have a hard permission of, say, like maybe 10 or 20 processes, nobody can go and invoke millions and millions, causing your application to crash. And then after everything, we clean everything up. We remove our C group because it serves no purpose there, and we are done. So going back to our session. So after C groups, I said, they apply the various limits, and namespaces are for isolation. So there are different namespaces to isolate different things on your system. Each namespace gives the process a view of the world. So the process in the namespace will think it only sees what the namespace shows to it and nothing outside the system, right? And together, all of these things, C groups and namespaces together, give you that kind of an environment in a container where it feels that it's running all by itself, when in reality it's like just another process which is running on your system, right? So some of the namespaces that we have is, the first one is the PID namespace, the process ID. So any process in a new PID namespace which start with 1, like the system init. Then there's the mount namespace, which will let you change your mounts, file mounts. So you can have your own devfs, you can have your own root file system and whatnot. This is how you have containers running with abstracted file system. Then you have the user namespace, which will give you the privilege isolation. So most common example of this, if you're using Docker, is you can be a non-root user on your system, but then if you run like an Ubuntu image, you'll be root inside. So this is how we can map, say, my UID with the root UID inside the user namespace in that container. Then there's the UTS, which is the Unix time sharing namespace, which will give you a separate host name and a separate domain name, thereby separating your application from the rest of your system. You also have the network namespace, which will give you your own network. So whatever things you do with Docker, you create your own network, like it may be a bridge network or something like that. You have your own IPs and everything. That is possible through the net namespace. And then we have the IPC, which is the isolated shared memory. So like if there's inter-process communication happening, you can section off a slice of it exclusively for your the container. So it can't see anything that is happening outside. It won't be able to interfere with other processes which might be running in other containers or any of the processes running on your host system. And now, we'll go for a demo. We'll try to see how each one of these namespaces work and how they are leveraged to make the container experience available to you by the container runtimes that are in existence today. So this repository, I'll share the link with you. So I have 5 tags. So each tag corresponds to each namespace. We'll run the program before and after to see kind of how it is affecting all those things. All right. So in the first piece of code that we'll be looking at. So this is a very, very simple example. This is not a lot happening here. We'll go over the basic structure of the program, and then we'll just build upon it. So we have a program which typically runs like you would run with Docker. So Docker run Ubuntu bash, similar to that. So the trick here is we first launch a program, and then we fork and launch ourselves. This is needed because if we want to launch in a new PID, the new process must be 1. And if I do, say, like an unshare call and put the spawning process into the namespace, it won't have a PID of 1 because it will already have a PID in the host system. So we need to spawn a new process, which we are doing over here. So we are giving it the new PID flag, and we are forking ourselves. And then inside here, we are not doing pretty much anything. We are just waiting for the control C, the sig int or the sig term, so that we can safely exit. And we'll be looking at the PIDs of the run. So the run will be the first thing that is invoked. Fork will be the second thing that's invoked. So we'll try to see what difference we get. Oops. There you go. So see, so when we first invoked, the run function got executed as PID 14,103, which is a PID on my host system. And then I forked itself with the PID namespace. It got the PID 1. So the fork function, the process which is running fork, sees itself as the init process of that system. It doesn't have anything apart from that. And that's how we achieve process isolation. Moving on. We now will look at the mount. So we have added another flag here, NS, which is for the mount namespace. And here you will see that I have a folder with a bunch of file systems from some of the common operating systems that we use today. And we can specify any one of those. And what we are doing is we are using the pivot root system call right here. So basically, the way pivot root works and the way it is different from chroot. So I think most of us are familiar with chroot. So chroot will allow you to change the root directory for that particular running process. But there is this vulnerability where if you do the certain system calls, like the double dot forward slash to go to a parent directory, you can probably escape out of the chroot jail. So in this case, what we do is we first create a hidden folder called as put old, where we are going to mount the existing root. And we also create a new root where we have our current directory. And then basically we switch it. So the current root goes into put old, and the new root becomes the current root. And finally, we just detach the put old. So there's no trace. There's no way which you can escape out of it. And that's probably it. There's some helper functions, but it's not very important right now. So let's try to run this again. We'll build this again. And now when I run this, you'll notice that now I'm actually at a bash shell where it says root at my host name. Similar to this, we have PID 14190 as the parent PID. The new PID is 1. And if I do something like psaf, you will see that there is nothing else running apart from that process. So the proc self-exec is the forked process which we launched up here in the run function. This is the one which became the init. The bash in which we are right now has become PID 7, and the psaf itself was bit 10. So now we have a container which is running with an isolated process and also with the isolated file system. You can also check, so like if you do cat etc OS release, so this actually shows up as Ubuntu 24.04.1 LTS, but if I go back to my host name and I do that same command, you'll see a different output. So there you go. I'm actually, the host is 22.04, but inside the container, it was coming as 24.4. You can also do this with a different one. So like I can do Fedora, and it should just work fine. And this is how you have process and file system abstraction. Now on to 0.3. So now, up until now, if you notice, we had to do a sudo to run each of our commands because we didn't have privilege to do all these namespace isolations, right? But ideally, like when you use Docker, you don't have to do sudo a lot of time. Like it runs rootless, and I think that is how we would have prefer our system to run as well. So for that, what we can do is we can now also clone the user namespace. So now I don't anymore belong to the host user namespace. I'll have my own user namespace, and I'll also map my current UID with 0 inside the container, and also the current group ID with 0 inside the container, which will effectively make me root. And once we do that, we'll no longer need sudo to achieve the same result. So you build it, and now we can just run it without sudo, and it just works fine. And I think most of the process output will be similar because we are already into that, right? And then what we have here. All right. So up until now, if you notice, the host name of the container is similar to what is of my, the host name of the container is similar to my host name. So like this is the container right now. So if I do host name, it shows up as Lima GCR because I'm using Lima to run this. And then again, if I do host name on my VM, again, it's the same, right? But this is not ideal. I would like each of my container to have a different host name as Docker does it. So now we also clone the UTS, which allows us that feature, and then we are also generating like a 12-character hexabyte because we are trying to be similar to Docker. And if we were to build and run this again, see, I got a different host name this time. It's not the same as the one on my system, and it's distinctly different. All right. Now, I think we have one more tag. Let's see. Yeah, I think we have the IPC namespace as well. All right. So for the IPC namespace, what we can do is we can see a simple example where we can create a shared memory, like say of a megabyte for two processes to communicate, right? And we'll see if it is also visible inside our container or not. Like with an IPC clone, it should not be, but the last example didn't have it. So I can just say IPC MK. And so you see, I actually have a shared memory segment with this ID and a shared memory ID of 0, which is currently on my host machine. And we can quickly go back to our container, and let's try the same command again. So you see, the shared memory segment which we created on our host system is actually visible inside the container, which is not the appropriate behavior because it's not completely isolated. So now that we have the new IPC, we can just rebuild our code, and we can have it run again. And if you try to do that again, you see that there exists no shared memory. So this is achieved by cloning the new IPC namespace, right? So yeah, I think yeah, so I think that's all there is to the demo. So I wanted to also include the net namespace, but to do it is not very simple because you have to create a bridge network and everything, which becomes more complex. And I think we didn't have enough time. So for the purpose of this demo, we were able to see how with the PID namespace, you can get your own process ID tree with your process being the init. With the mount namespace, you can have your file system level abstractions. With the user namespace, you can actually have a privileged access within your container, but you can still be non-privileged outside. You can also change, like this doesn't have to be 0. So if you have a new user, you can also put in that ID so that you go as a non-root inside that container. Then we saw the UTS namespace, which gives us the ability to create a unique host name and a domain for our container. And finally, the IPC namespace, which gives us dedicated inter-process communication, which is restricted to that content. And yeah, I think that's all there is to the demo. If you'd like to hack with the code yourself, please scan the QR code. If you like to get in touch with me, you can also scan the other QR code. And yeah, please, the feedback, pull requests are welcome, and we'll try to make it better. I've also included the Lima YAML file so that you don't have to do complex VM setups. You can you just clone it, and it should be ready to go. There's also one more thing that I think I didn't talk about, which is in the repository. So if you're wondering about how I got all the images, like the rootfs, so this is a small utility that I've created. So you can just use it. I think it's described here, yeah. So you can build it, and then you can just point it to any Docker image of any operating system that you want, and it will actually output the rootfs for you in the location of your choice, and then you can use that along with this code to try it with your experiments and stuff like that. And yeah, I think, yeah, that's all there is to it. Thank you.
Thank you so much, Ajitem. We are up for questions now, so you can grab your mobile phones not only to scan QR codes, but also ask some questions. So far, there is just one very brilliant feedback, so you can enjoy it in full thing. And I can also just include my excellent feedback. It was also brilliant. I completely agree. And also kudos to your bravery for the live demo, and it worked out perfectly well. So.
Actually prepared it last night.
Whoa, that's a double kudos for that bravery too. What is Lima for folks?
So Lima is a CNCF project which lets you run containers or even VMs on your machine. So you can either have your machine run inside Docker, or you can have it run inside QEMU, as I'm doing it. And I think it works really well on Mac because it abstracts all the complications. And I think I can also show this to you. It also allows you to describe how would your virtual machine be like, so you can specify an image, the architecture, the CPU memory configuration, the mount points, and so many other things. So it makes it it's kind of like Vagrant, but I struggled a lot with Vagrant, especially on the M series. It doesn't have good providers, so this worked out for me.
Wonderful, thank you. So the next one is rather a clarification question, if the person got it right. So the concept is you clone namespaces and then you map entities from the host system to the cloned namespace like users.
Yes. So namespace, so whenever you do a clone, so I think standard syscall is called as share and unshare, but with Go it's a bit difficult, like it's weird. So they say clone and unshare. So whenever you clone something, you make it inaccessible to others. So like if I clone the PID, only I get PID and no one gets the PID, right? And if I do unshare, it means that I myself go into that new namespace. So the reason we can't do unshare is because, like I said before, if I myself become init, I can't because I have a root PID. But then to answer your questions, it depends on what you are cloning. So like for users, you need a mapping because the container needs to know who is being linked to what, but that's not always the case. I think for file systems also, you can create mounts, I think, as you saw here. So once I do the new NS, I can mount proc and then dev, temp, or anything else that you want. You can also map sys and do an implementation of cgroups, but it's not a requirement for each of the namespace. So like for PID or for UTS or IPC, you don't really need to map or mount. It depends on what you're trying to do.
Wonderful, thank you. How can we create a virtual file system in the container?
I think I probably need more context on it because right now we can do either this or you can also have a path and mount it at a different path like Docker does it with your volumes. So there are both ways of doing it. I'm not sure if I'm able to answer it because I'm not sure if I'm understanding it completely.
Yeah, but then, I mean, you're still around until
we can still talk later. Like we can also talk on the sidelines. That's fine.
Awesome, thank you. So why did you have to clone the existing process namespace and not start a new one?
I think we started a new process when we cloned namespace. So, okay, so I think let's come to a simpler analogy. So let's assume I am operating a playpen, like a playground for kids, right? And for each kid that comes in, I need to give them a dedicated sandbox so that they don't fight with each other. But at the same time, I need to be present so that I can monitor all the kids who are playing inside their sandboxes. And then when they leave, they can clean up or like not mess around, right? So if I don't like clone, so if I say unshare, so what unshare means is that the kid is going in the sandbox and I myself also am going into the sandbox along with them. So now there's nobody left back to clean up. So if we do an unshare call and have both the processes running in the same PID, so if the child process, for example, crashes, there will be no one left behind to clean up after it, which is why we first launch our first process and then fork with the namespace so that I always remain in control on the host system. So if there's something wrong happening, I can take care of cleaning up the resources and certain other things, which is why that is the dynamic. But for I think others, you can also do an unshare. Like if you want a simple bash, you can just say unshare and then say the flag name and run bash, and you'll be able to see the result readily if you don't want to go to all that complexities.
Great. So you answered all the questions. I will leave the feedback just
thank you.
Forever. No, just kidding. Thank you so much for being here, for answering all the questions, for giving a brilliant talk and demonstration. Have a lovely rest of the day.
Sure.
And you all, of course, as always, you know the game. A round of applause. Yeah, they've just popped up one last question. Maybe we can just sneak that. If you want to leave already, you can, of course, do. But if there are there any recommendations?
Yeah, so there are some things that I would recommend. So there is a talk by Liz Rice, I think it's from years ago, where she first touched on this topic. And I think there's also an excellent blog series on Medium by Ed King. So what he does is he's creating this tool called as NS process, and he's doing it slightly in a different way. But essentially it's the same. He also has a section where he's also been able to implement the networking. But as is with software, that code is not working as expected today. Like even this code, if you try to run it on Ubuntu 24, it has some app armor changes and other policies. Like it's on kernel 6.8, right? So it become more difficult to get this to run, which is why I'm running it on 22. So I think with 24, we'll have to make some more changes. But I think, the series by Ed King and the video by Liz Rice, I think they are excellent things. If you want to run more about pivot root, I think there is the EU BSDCon talk by Adrian Steinman. I think it's from 2001 or 2002, where he talks about the pivot root syscall, which was first originated in FreeBSD, and then later it came back to Linux. So I think those are very good resources. And like all of this stuff is like very old, like decades old. It's just being more popular today. So you'll find a lot of literature on this if you search.
From ContainerDays Hamburg, This video is proudly presented by Dux IT.